Now we turn to a type of sand that requires a very special set of circumstances for its deposition. From here, we'll leave the environment of rivers and streams altogether. In fact, we leave the influence of water largely behind as well, at least for the moment. Actually, most of the Earth's desert regions are in a state of geologic equilibrium, covered by barely eroding bedrock or sandy plains with gravelly deflation lags from which all fine material has been winnowed away by the wind. But in some areas, both modern and ancient, large amounts of sand in the form of aeolian dune fields, such as these, have been deposited. And after certain difficulties in interpretation were overcome,
these aeolanites, as they're called, were recognized as forming excellent and unique petroleum reservoirs. The most impressive examples are interpreted to have had their origin in areas like the one we just saw, in great sand seas that today make up a quarter of the world's desert regions.
Using our observations, then, of the major present-day desert environments, we see that two things are required for the formation of dunes: a large supply of sand and wind strong enough to move it. By looking closely, we can see that sand is transported close to the ground, moved along mainly by the bounce-ricochet energy transfer of saltation, and by avalanche down the steep dune face. This results in a dominance of cross-stratified bed forms. Since the actual process of traction is similar in both aeolian and aqueous environments, the sedimentary structures and internal geometry of dunes may appear to resemble those seen in alluvial bars. That is, near horizontal toe-set laminae, dipping foresets along the slip face, and top-set layers that dip gently into the current.
the constant winnowing of sand by the wind makes it very well sorted and devoid of most fine silt and clay. But deserts are also quite variable environments and produce no predictable vertical arrangement of facies. Our concept of the entire aeolian environment too often is that of a massive, thickly cross-bedded homogeneous sand deposit, such as the well-known Navajo sandstone of the western U.S. We should keep it in mind that the uniform dune sands with their thick, high-angle crossbeds are just one subfacies of the aeolian environment. There may also be sand sheets, which occur at the margins of dune complexes and are characterized by low-angle crossbedding. Or instead of these, we can often find a river, lake, or marine facies where dune fields develop near alluvial plains or along an arid coastal margin. These can produce a vertical sequence in which wind and water-laid strata are intimately mixed. In this kind of sequence, it can be almost impossible to strictly separate aeolian, alluvial, or marine deposits.
If we turn our attention to the dune field itself, we'll notice that some areas between individual dunes contain standing bodies of water that trap clay and silt, which would otherwise eventually be removed by deflation. Evaporitic interdune areas, found in both arid inland and coastal sabkha environments, are similar, but have dissolvable salts and carbonate mixed in with a fine detritus. If there is a constant wind blowing from one direction and dunes are migrating, these interdune areas won't remain sand-free very long, and only small pod-like shale or evaporite bodies, usually less than 2 meters thick, will be preserved.
In the sedimentary record, the aeolian facies is usually dominated by medium to fine-grained quartz sandstone. Individual quartz grains are rounded to well-rounded and well-sorted. There are essentially no pebbles and very little silt or clay. This facies is generally so barren and lifeless that the chance of finding plant roots and burrows in cores is almost negligible. In contrast, the interdune facies can be the site of intense organic activity and may provide the only important biostratigraphic reference horizons within thick sand sequences. In some cases, their organic content may be high enough to have formed local petroleum source rocks. As to the sedimentary structures found in these sands, they can vary. But as we've mentioned, the most conspicuous feature by far is the large-scale high-angle crossbedding. Generally, this crossbedding varies in the amount of dip, not in overall direction. This tells us that, interestingly enough, it has been Barchan and transverse dunes those that are unstable and migrate continually, which have been the most preserved.
But in the rock record, completely identifiable individual dunes are almost unknown. Each is most often truncated at the top by the toe set of the overlying dune. It is, therefore, usually a useless attempt to try and recognize individual dunes, even an outcrop. Without outcrops, as always, cores provide the geologist with a limited subsurface exposure of the rocks themselves. In known eolinite reservoirs, cores have consistently shown the characteristic medium to large-scale cross-bedding with high-angle foresets that often exceed 30 degrees. Desert dune foresets most often tend to occur in cross-bedded sets from 1 to as much as 100 feet high. When stacked together, they form monotonous sand sequences up to hundreds of meters thick in the sedimentary record.
Let's look for a moment at the log curves which show the characteristic dip meter and gamma ray responses. The gamma ray log shows a rather clean, even profile, broken by occasional sawtooth kicks with sharp bases and an upward decrease in shaliness. These occur at fairly regular intervals, in this case about every 50 feet. They are due to a fraction of clay and mica, which is blown further from the dune crest and becomes part of the toe set layers at the dune's base. Now, on the dip meter log for these deposits, the most obvious and diagnostic motif is an upward increasing pattern that measures the increasing slope of cross-bedding from the toe set to the foreset of a particular set. This is the blue motif again, that indicates local current direction, in this case wind direction. If we compare the gamma ray log, we see a close correspondence between the mentioned kicks and the so-called blue dip motif. Both logs respond, as we should expect, to the presence of finer material in the lower part of the dune. The low-angle green motif, meanwhile, represents the dune toe set beds and corresponds with the sharp base of each kick on the gamma ray log. Essentially, then, the dip meter log shows us where we are on the dune. Green for flat toe sets, blue for upward steepening, lower foreset. Notice that we normally don't see any red pattern in dune complexes, that it is replaced by large-scale uniform dips of the upper foreset beds. This uniformity in both magnitude and direction is far greater than that normally found in water-laid deposits.
As to their overall geometry, aeolian sand bodies are highly variable, and whatever shape they acquire with burial is not diagnostic of the depositional environment. This satellite image of eastern Iran shows the irregular margin of a single dune sand body. Since we're here, we should probably also note several other major desert facies, namely alluvial fans, braided streams, and playa lakes. Such sand bodies may be limited by mountains and coastlines, as shown by this image of the Namibian desert along the southwestern African coast, or by lakes and rivers. This Landsat image of the Nebraska sandhills shows that the entire dune field shape is determined by the Niobrara River on the north and by the North Platte River on the south. A deposit like this, upper surface, with the specific dune shapes, leveled out by the waves of a marine transgression.
All in all, though their reservoir properties are usually good to excellent, dune sands are not an abundant facies in the sedimentary record, and have acted as the sites for petroleum accumulation in only a relatively few instances. At the same time, there are several important eolinite reservoirs in the western U.S. The Weber, Ten Sleep, and Nugget sandstones are the better known of these. Your manual discusses the Painter Field in the Nugget, which was discovered in 1977 along the overthrust belt of western Wyoming and has been proven to contain over 1 billion barrels of oil.
The truly classic, well-studied Aeolian play, however, is the Permian-Rodriguez group, the most important gas reservoir in the North Sea region. The sands of the Rodriguez were deposited in an arid evaporitic basin that lay just north of a tectonic uplift stretching southeast from Ireland to Germany. They built up over an erosional surface of faulted Carboniferous coals, which later acted as a source for the natural gas, now produced at Viking Field, for example. The dunes occupied a transition zone between the conglomerates and sands of the alluvial fan and seasonal braided stream, or wadi environment, and the evaporitic red mudstones of the Sabkha Playa lakes to the north. The transition, which takes place over some 200 kilometers, is also seen in the overall transgressive vertical sequence, where wadi sediments are successively overlain by those of the dune, Sabkha, and desert lake environments. This last became the Zechstein salt, which provides an excellent upper seal for the fault traps in the area. In terms of reserves, it is estimated that the Viking Field complex contains some 3.6 trillion cubic feet of gas. This complex lies close to the northern limit of dune sands, where the Rotliegendis contains some interdune Sabkha and wadi deposits. Reservoir sands are in both the Aeolian and mixed Aeolian wadi facies. The quality of the reservoir, meanwhile, is highly variable and strongly related to specific facies. The best permeability and porosity are found in the Aeolian facies, while reservoir quality is intermediate in the mixed sands of the playa sediments, and much poorer in the playa and braided fluvial facies, where clay particles and cementation have destroyed most of the primary porosity.
In general, dune complexes are often difficult to identify in the subsurface. But there is one last non-marine setting whose sediments can be even more difficult to distinguish from their marine counterparts. Let's go out for a minute and have a look at it. Sand depositing lakes occur at almost every climatic regime on Earth, at almost every latitude, from the equator to the Arctic Circle. This makes for a tremendous variety in specific sediment type and discourages easy generalizations. In a large, perhaps great lake, we can sometimes find deltaic, barrier island, lagoonal, and even subaqueous fan deposits. Because of this, we really can't treat lacustrine facies in the same way, with the same degree of detail, as we did the Aeolian and fluvial environments. But there are a few broad aspects we might talk about.
For example, most lakes have their coarsest sediments along their shoreline margins, while silts, mudstones, carbonates, or evaporite facies characterize their centers. Since most perennial lakes eventually become filled in with sediment, their overall depositional history is regressive, with finer grain, deeper water material progressively buried by coarser detritus of the nearshore and shore environments. Perennial lakes in relatively temperate climates have provided the best self-contained hydrocarbon systems, with both source rocks and reservoir rocks.
The ideal concentric facies pattern looks like this: a fining inward sequence that begins with the coarsest material in a shoreline facies. This rims the lake on all sides, grading through silt into carbonate-rich rocks or mudstones in the depositional center. Such a pattern is rather well shown by the large mid-Cenozoic lakes of the Rocky Mountain region, such as Lake Uinta, which persisted for some 13 million years.
This ideal facies pattern, which changes from offshore muds to good porosity sands being deposited at the lake margin, should sound familiar. It is, after all, just what we see in a large number of shallow marine basins, or along coasts like this one. In many respects, large, geologically persistent lakes might be thought of as, well, small inland seas. Reservoir sands can accumulate in deltas, shoreline beaches and bars, or in basal turbidites, with an entire suite of sedimentary structures normally found in similar marine facies. Because of this, there can sometimes be confusion on how to distinguish lacustrine deposits from those that were laid down in marine environments.
The obvious criterion for identifying lacustrine deposits is the absence of any marine fauna, particularly in silts and muds formed by suspension settling. The presence of non-marine fossils, certain species of gastropods, fish, and land vertebrate remains, will for the most part act as telltale clues. At the same time, calm, unmixed lake water, like that in restricted seas, may develop seasonal or permanent stratification, and life forms that live in the surface waters or along the lake margins may wash or sink into the deoxygenated depths. Organic rich muds created in this way can form important petroleum source rocks.
Though lakes are only minor features in the stratigraphic record, there are several major petroleum provinces in China, Brazil, Australia, and the American West that have both source rocks and reservoirs in lacustrine sediments. We should also be aware that sediments which originated in Rift Valley lakes, such as those along eastern North America and East Africa, have begun to attract the attention of exploration geologists. In western Eocene, the newly risen mountain ranges of western Colorado, Wyoming, and Utah helped cut off the exterior drainage of several large river systems, encouraging the development of what has been called two of the Rocky Mountain Great Lakes. The largest and most persistent of these was Lake Uinta, which covered the entire Uinta Basin, an intermontane tectonic depression of over 8 square miles, which lay to the immediate south of the rising Uinta mountain block. The resulting lacustrine facies were complex, consisting of dolomites in the open basin center and deltaic and interdeltaic sands and carbonate flats at the margins. Both are part of the Green River Formation, well known throughout the world for its oil shale potential. Present petroleum production comes from the marginal lake sandstones. The configuration of facies is shown here. A continuous building out and retreat of the original lake margin has created a complex interfingering between open lacustrine and deltaic deposits. This has meant a very intimate juxtaposition of source and host rocks within this single formation. Today, the basinal facies is often an oil shale, thinly laminated and extremely rich in algal kerogen. It is this rock which is the focus of oil shale operations in the U.S.
Lakes like Uinta, whose facies have been well preserved and have come to hold large amounts of petroleum, are rare in the sedimentary record, but perhaps not so rare as we once might have thought. In North America, for example, geologists are beginning to take a serious look at the petroleum potential in lake deposits known to exist along two major rift basin trends, the late Precambrian Key of north-central United States and the early Mesozoic Newark Rift system that stretches from Florida to New England.
This then concludes our cursory but we hope instructive survey of non-marine depositional environments. We've looked briefly at 5 environments that deposit sands which have acted as reservoirs for sometimes giant accumulations of oil and gas. Alluvial fens, braided streams, meandering rivers, aeolian dunes, and large lakes.
So we have seen that many non-marine sandstones have excellent porosities and permeabilities, and that even though continental environments are often lacking when it comes to local petroleum source rock, geologic history has been complex and sometimes helpful enough to overcome this.
This program has been sponsored in part by the following companies: